Imagine absolute stillness. Not the quiet of an empty room or a peaceful night, but something deeper. A silence untouched by wind, sound, or breath. Now take away the room. Take away the air. Take away space itself. No light. No dark. No up. No down. No distance, because there is nowhere to go. No time, because there is no ticking clock. There is no before, no after. Just a kind of waiting that never began and never ends. This is what we mean when we ask, what was there before the Big Bang? It's not just a question of curiosity. It's a question that presses up against the edge of what humans can think about. Every instinct we have, every part of our brain wants to imagine something, a cloud, a field, a void. But there was not even a void. A void is something. And before the Big Bang, there wasn't something. There wasn't even nothing in the way we usually understand it. This is hard to grasp because we live inside time. We wake, we sleep. We count the minutes and years. Everything we know has a beginning and an end. You were born. I was created. Stars are born in swirling gas clouds, and they die in dramatic explosions. But the Big Bang? That was the beginning of beginnings. And before that moment, even time itself didn't exist. Not as we know it. So how can we even ask, what was there before? The question is a paradox. It's like asking, what's north of the North Pole? Or, what happens after the end of the last page? These questions don't have answers in the usual way. But even so, they point to deep truths. When we ask what was there before the Big Bang, we're really asking, did something cause the universe? Was there a spark, a reason, an origin of origins? And here's where things get interesting. Some physicists believe that the very question is meaningless. They say time itself began with the Big Bang, like the opening frame of a movie. Asking what came before is like trying to rewind a film into the part where there's no film at all. But others believe there is something to say about before, and that something may be stranger than we ever imagined. So tonight, close your eyes and drift into the deepest kind of silence. Imagine not a starless sky, but a world with no sky at all. No stars, no space, no ticking clock. Now picture the tiniest flicker, not even a flash, more like a whisper of potential, a ripple in something that doesn't yet exist, a pregnant pause in the eternal hush. That flicker is where we'll go next. Prepare yourself. Let's begin. When you gaze at the stars, you're looking back in time. Every beam of light from a distant galaxy has taken millions, sometimes billions of years to reach your eyes. In a way, you're watching ancient stories unfold across the sky. But what if you tried to look back even farther? Not to the first stars, not to the swirling hydrogen of the early universe, but to the very start of it all. You'd hit a wall, not a physical one, but a boundary in our understanding. The Big Bang marks the beginning of space and time as we know them, and trying to peer beyond that point is like trying to read a page that hasn't been printed. It's where physics, as we currently understand it, breaks down. This moment, the beginning of time, is not like any other beginning. It's not like turning on a light or planting a seed. Those are events that happen in time. The Big Bang created time, and that makes all the difference. In the earliest fractions of a second, the universe expanded faster than light in an event known as cosmic inflation. Space ballooned out of nothing, filling with energy, particles, and eventually galaxies. But if inflation happened, then what set it off? What caused the spark that lit the universe? Here's where the edge of physics starts to blur. General relativity, Einstein's beautiful theory of gravity, describes how space and time bend and stretch. It tells us how stars move, how black holes form, and how the universe expands. But when we push it back to the very start, we find something strange. The math breaks. It predicts a singularity, a point where density becomes infinite, and the laws of physics simply stop working. At that singularity, gravity becomes so intense that it warps space and time into a single tangled knot. Our equations spit out infinities, like trying to divide by zero. It's the ultimate syntax error in the code of the cosmos. And this is why physicists say the Big Bang wasn't an explosion in space. It was the creation of space itself. And time, that too came into being. It didn't tick forward from a clock behind the curtain. It started right then and there, born in the very fireball of existence. So when people ask, what happened before the Big Bang? We have to pause. Because according to general relativity, there is no before. There's no timeline to look back on. The Big Bang isn't an event that happened in time. It's the moment when time began to happen. But there's a problem. General relativity doesn't know how to talk to the very small. That's the job of quantum mechanics, which governs the world of atoms, particles, and probabilities. And when the universe was smaller than a subatomic particle, we need both theories to work together. But they don't, not yet. This is where modern physics stands at a great crossroads. We have two magnificent theories, relativity and quantum mechanics, that both describe reality incredibly well. But when we try to put them together to explain the birth of the universe, they clash. So what's the answer? What lies beyond the singularity? Do time and space emerge from something deeper, something even more fundamental? Some physicists believe that if we had a theory of quantum gravity, it could describe what happened in that tiniest instant. It could reveal what the universe was before it was a universe. Was it a quantum soup? A flickering field of pure energy? A shape in higher dimensional space? We don't know. But we're trying. Every particle smashed in a collider, every satellite peering into the microwave afterglow of the Big Bang, every signal captured from the edge of the universe. These are all part of humanity's search to answer a question we may never fully grasp. What does it mean to come from nothing? And if time began at the Big Bang, what kind of nothing birthed time itself? As we move into this mysterious territory, we leave behind the clean equations of Einstein and step into the realm of uncertainty, a realm where particles pop in and out of existence like sparks on a dark ocean. A place where something might come from nothing, not because of magic, but because of the deep structure of reality itself. And in that shimmering field of possibility, something began to stir. Imagine staring into a pond at midnight. The surface is perfectly still, undisturbed, silent. Then, without warning, a ripple dances across the water. No pebble was thrown, no wind disturbed the air. It just happens, quietly, unexpectedly. Now picture that ripple not in water, but in nothingness. A flicker in the vacuum, an event that shouldn't occur, but does. This is the strange world of quantum fluctuations. To understand what might have existed before the Big Bang, we must leave behind the comforting laws of classical physics and venture into quantum reality, where things behave in ways that defy all common sense. You see, even when we remove everything from a space, every atom, every photon, every wisp of heat, what's left behind isn't truly empty. According to quantum mechanics, the vacuum itself is alive with possibility. It seethes with uncertainty, pulsing with tiny, momentary disturbances called fluctuations. Particles and antiparticles flicker into existence, live brief, ghostly lives, and vanish again. So fast, that the laws of physics barely notice. This ever-churning quantum foam might have been the first hint of being, long before stars or galaxies, before time itself. In this pre-Big Bang haze, nothing was stable, nothing was still. It was not a place, not a moment, but a quantum potential, an uncertain soup of probabilities. And from this bubbling chaos, something extraordinary might have emerged. Physicists theorized that under certain conditions, a quantum fluctuation could grow. It could gather energy, inflate rapidly, and become an entire universe, a process called quantum tunneling. Like a bubble forming in boiling water, a whole cosmos might tunnel through the fabric of quantum nothingness, expanding with breathtaking speed. Could that be what happened with our universe? Some versions of quantum cosmology propose that the universe is a self-contained fluctuation. That means it didn't need a cause, it didn't need a trigger, it popped into existence because quantum rules allow it to. There was no outside force, no hand reaching in, no explosion in space, just a sudden bloom in the strange landscape of possibility. This idea is both comforting and unsettling. It suggests that something can come from nothing if that nothing is understood through the lens of quantum mechanics. Not an empty void, but a field of infinite potential, waiting to become reality. But wait, how can that be? Doesn't that violate energy conservation? Here's the twist. The total energy of the universe might be exactly zero. Positive energy, like matter, light, and motion, is balanced by negative energy, like gravity. The sum cancels out. It's like borrowing from a bank with perfect bookkeeping. The debt and the loan cancel each other. So in a very real way, the universe could be the ultimate free lunch. And because quantum mechanics doesn't forbid it, maybe it had to happen eventually. If enough time, or something beyond time, existed, then a universe was statistically bound to pop into being. And once it began, inflation took over, expanding that tiny bubble to cosmic size in a fraction of a second. But here's where the mystery deepens. In a realm without time, what does eventually mean? How can something happen when there's no clock ticking, no past or future? We may be trying to squeeze human logic into a place where it simply doesn't apply. Still, these quantum theories provide one of the most intriguing glimpses into what might lie before the Big Bang. A pre-universe not made of things, but of potential. Not a world with space and stars, but a roiling sea of probabilities, blinking and jittering in the fabric of reality itself. And then, a fluctuation crossed a threshold. It didn't just appear, it grew. Faster than light, faster than thought, it erupted into being. A universe wrapped in the laws of physics was born in silence and fury. And that moment, the first blink of something from the nothing, was the beginning of everything. What sparked that ripple? Was it a one-time event or one of many? Was there a reason, or was it just luck? We'll explore that next. If you could float through the emptiest place in the universe, between galaxies, beyond the reach of any star, you'd find something unexpected. Not perfect stillness, not absolute zero, but a low, gentle hum, a faint energy in the dark, a whisper from the vacuum. This is the truth that shattered our old idea of nothing. The vacuum isn't empty. It is, in fact, full of potential, of tension, of secrets. In quantum physics, what we once thought of as nothing is better described as a quantum vacuum. A seething field of invisible particles and antiparticles constantly appearing and disappearing, governed by uncertainty and raw possibility. So when we ask what existed before the Big Bang, we may not need to imagine a complete void. Instead, we might picture a false vacuum, a kind of high-energy, unstable something that isn't yet space or time, but contains within it the ingredients of both. This state, delicate and balanced like a tightrope walker, might have teetered, then fallen, into a more stable condition. That sudden fall could have released a flood of energy, igniting the inflation that caused our universe to expand from something unimaginably small to something vast and full of stars. Think of a hill. At the top, a ball rests precariously. That's the false vacuum, unstable but not moving yet. Then the ball begins to roll downhill. That's the phase transition. And at the bottom lies the true vacuum, our universe, expanding and cooling as the ball reaches stable ground. This process is not just theoretical, it fits with some of the deepest ideas in particle physics, including the Higgs field, which gives particles mass. Fields like the Higgs suggest that space itself has structure, that the vacuum is not a blank slate, but a layered, dynamic entity. When the vacuum shifted from high energy to low, it was like the universe exhaled. A burst of expansion occurred, stretching space in an instant, smoothing it, flattening it, cooling it. This inflationary phase explains why the universe looks so uniform in every direction, why space is so flat, and why we don't see relics of an earlier chaos. Inflation erased the wrinkles. And here's where the mystery deepens. If inflation began in one patch of this vacuum, what about the rest? Some theories suggest inflation never completely stopped. Instead, it continues endlessly in other regions, spawning an infinite number of bubble universes. Each bubble, like ours, stops inflating and cools into a distinct universe with its own laws of physics. This concept is called eternal inflation, a breathtaking idea that the Big Bang wasn't the beginning of everything, just the beginning of our part of the multiverse. Imagine a vast loaf of cosmic bread rising forever in an oven. Each bubble that forms in the dough is a new universe. Our universe is just one such bubble. Before our bubble formed, the vacuum outside was still bubbling, still foaming with potential. In that context, before the Big Bang doesn't mean before time began, but in another part of the inflating vacuum where different bubbles might already exist, or not yet exist. The false vacuum, then, might be the eternal backdrop of existence, timeless, limitless, brimming with the energy to create worlds. But what created it? That's a harder question. Some physicists argue that the quantum vacuum and the laws that govern it have always existed in some form, timelessly. They weren't created because the very notion of creation implies time, and time didn't apply yet. In this view, the universe emerged not from nothing, but from something deeper than space and time, a quantum field filled with tension and probability. That field didn't need to be created. It was, always. Others think the vacuum itself might have emerged from even more abstract principles, mathematics, logic, or even pure information. But we're not there yet. The physics is speculative, and experiments can only take us so far. Still, this picture of the vacuum as a restless, creative place is one of the most compelling we have. It shifts our understanding of what nothing really means. Not an empty box, not a blank canvas, but a roiling, pregnant field with the power to birth stars and galaxies. And maybe this has happened before, or will happen again. Because some scientists believe the universe is not a one-time event. They believe in cycles, in an eternal beat of birth, death, and rebirth. That's where we're heading next. Imagine a heartbeat so slow, so vast, that each thump lasts billions of years. Now imagine that heartbeat is not a heart at all, but the universe itself. For centuries, humans have imagined time as a straight line, an arrow flying forward from the past, through the present, into the future. But what if that arrow is really a circle? What if the universe is not a one-way journey, but a cosmic cycle, expanding, collapsing, and rebirthing over and over again? This idea isn't new. In fact, it's ancient. Hindu cosmology speaks of an eternal rhythm, universes being born, existing for eons, then dissolving back into a formless sea, only to rise again. In modern science, some physicists are returning to this idea, with equations to back it up. One version of this is the cyclic model. It proposes that the universe goes through endless phases. A Big Bang, followed by expansion, then a slow cooling and eventual collapse, followed by another bang. Each cycle wipes the slate clean, but not entirely. Tiny imprints from the previous universe might echo forward into the next, like faint memories in the fabric of space. But how would such a collapse happen? Well, gravity is the key player. Right now, the universe is expanding. Galaxies are drifting apart, and space itself is stretching. But what if, after billions or trillions of years, that expansion slows? If gravity overcomes the momentum of the original expansion, it could pull everything back together in a big crunch, a colossal reversal where galaxies race toward one another, stars collide, and everything collapses into a single point. That point could be the seed of the next universe. Sound familiar? It mirrors the singularity we associate with the Big Bang. But in this model, the singularity isn't the absolute beginning. It's just the next phase in an eternal cycle. Another model takes a different route. It's called the ekpyrotic universe, from a Greek word meaning conflagration or cosmic fire. This theory emerges from string theory and suggests our universe was born not from a single point, but from a collision. Imagine two enormous invisible sheets, called brains, drifting in a higher dimensional space. When these brains collide, the impact unleashes a burst of energy, our Big Bang. After the collision, the brains bounce apart. Then, over untold time, they drift closer again. Eventually, they crash once more, triggering another bang, and another, and another. A universe without beginning, without end. Just an infinite rhythm of cosmic rebirths. What makes these ideas so fascinating is that they could, in principle, be testable. Some models predict tiny patterns, gravitational waves, wrinkles in the cosmic microwave background, or specific particle signatures that we might someday detect. Evidence, perhaps, of a universe older than the Big Bang we know, but we must tread carefully. These models are not yet proven. They're still speculative, built from mathematical beauty and deep intuition. They're bridges between known physics and the mysteries beyond. Yet they offer hope, because if our universe is just one heartbeat in an eternal pulse, then the question, what came before the Big Bang, has an answer: another universe. Maybe one much like ours, maybe radically different, maybe governed by different physical laws, but still, a world, a cosmos, and this changes everything. It means the Big Bang wasn't the first moment, it was just this moment's beginning. The universe may not need a cause because it never truly began. It's always been in motion, cycling through phases, evolving across aeons beyond imagination. This view gives us a strange kind of comfort. It tells us we're part of something grander than a single explosion, a cosmic heartbeat that stretches across eternity. But what if our universe isn't alone? What if, instead of just one loop repeating, there are countless loops, running side by side? What if there's not just a cycle, but a multiverse? That possibility lies ahead. Imagine blowing a soap bubble on a quiet afternoon. It floats, shimmers, drifts. Now imagine not just one bubble, but billions. Some tiny, some vast, some still forming, others already popped. All drifting in a space you can't see, all completely sealed off from each other. Now imagine that each bubble is a universe. This is the heart of the multiverse hypothesis, one of the most extraordinary and controversial ideas in modern physics. According to this theory, our universe, the one with stars and galaxies, planets and people, is just one bubble in a cosmic foam. Beyond the edge of what we can ever observe, other universes may stretch into forever, each with its own Big Bang, each with its own laws of physics, each one entirely separate. This isn't science fiction. It's a serious, though still speculative, consequence of some of our best ideas in cosmology and particle physics. It arises naturally when you look at what might have happened before or beyond the Big Bang. One pathway to the multiverse comes from the eternal inflation model we touched on earlier. In this theory, the process of inflation, rapid expansion of space, never completely stops. It ends in isolated pockets, like ours, where a universe cools and forms stars. But outside those pockets, inflation keeps going. More and more bubbles form, eternally, each becoming its own universe. Some are similar to ours. Others might be so different that the physics inside them is unrecognizable. In one universe, gravity might be too strong for stars to form. In another, atoms might never exist. In yet another, time might flow in 2 directions, or space might have more than 3 dimensions. If this multiverse is real, then almost every possible version of reality is playing out somewhere. Another route to the multiverse comes from string theory, one of the leading candidates for uniting quantum mechanics and gravity. String theory suggests that the fundamental building blocks of the universe aren't particles, but tiny vibrating strings. These strings vibrate in many different ways, and each vibration produces different physical properties: mass, charge, and more. But for the math to work, string theory requires extra dimensions, not just the 3 of space and 1 of time we're used to, but as many as 10 or 11. These extra dimensions are hidden, curled up tightly beyond our perception. And the way these dimensions fold and twist can create entirely different sets of physical laws. The result? A vast landscape of possible universes, perhaps 10 to the power of 500 different versions, each with its own unique reality. In this string theory multiverse, the Big Bang wasn't a singular creation, but just a local event. One pocket where the right conditions came together to spark a universe. Ours. Some scientists go even further, proposing that mathematics itself generates the multiverse. If every consistent set of mathematical rules describes a potential reality, then all those realities exist somewhere. The idea is called the mathematical universe hypothesis. In this view, our universe is real because the math is self-consistent, and so are countless others. Still, not everyone is convinced. The biggest challenge with the multiverse is that it may be unprovable. By definition, other universes would lie beyond our observable horizon. We can't touch them, we can't see them, we can't interact with them. If no evidence can ever reach us, can the multiverse ever be more than just an idea? But that doesn't stop the speculation. Because if the multiverse is real, then we no longer need to ask, why is our universe so perfect for life? In a multiverse, every kind of universe exists, including ones where life isn't possible. We just happen to live in the one where it is. This is known as the anthropic principle. We observe a life-friendly universe because only a life-friendly universe could be observed by beings like us. It's a bit like finding yourself on a rare island in a vast, deadly ocean. You could marvel at how perfectly the island suits you, or you could realize it's the only place you could survive. So of course, you're there. The multiverse reframes the question, what was there before the Big Bang? Into something bigger. It asks instead, what lies beyond our universe entirely? And the answer might be more universes, different laws, endless realities, and somewhere, perhaps, a universe where something happened before the Big Bang we call our beginning. Maybe it was older, maybe it was stranger, maybe it even gave birth to ours. But to go further, we need a new kind of language, a way to describe the unseeable, a theory that goes beyond even strings and bubbles. We need to explore the deep ideas of higher dimensions and the strange world of brains. That's where we'll go next. Close your eyes for a moment. Now imagine that our entire universe, everything we know, from atoms to galaxies, is like a sheet of paper, thin, wide, vast, but flat. Now imagine another sheet floating nearby, and another, and another. Each one a universe, each one isolated, like pages in a cosmic book. This is the strange and beautiful idea of brains, short for membranes, from string theory and M-theory, which suggests that our universe might be just one of many floating in a higher dimensional space. In this picture, the Big Bang wasn't the birth of everything. It was a collision between brains. Here's how it works. String theory tells us that the fundamental components of nature aren't particles, but tiny, vibrating strings of energy. And for the math to work, these strings don't just vibrate in the 4 dimensions we know, 3 of space, 1 of time, but in 10 or even 11 dimensions. Most of those dimensions are invisible to us, either curled up tightly at microscopic scales or existing in directions we simply can't access. But in M-theory, which is a broader framework uniting different versions of string theory, some of these higher dimensions can be large. In fact, entire universes can float within them, each a 3-dimensional brain, like a soap sheet drifting in a greater, unseen reality. Our universe is one of these brains. It means that while we're stuck living on our cosmic sheet, gravity might be able to leak into other brains. That's why gravity seems so much weaker than the other forces. It may be diluted across multiple dimensions. Now here's where things get cosmic. According to the ekpyrotic model, based on these brain ideas, our Big Bang wasn't a beginning. It was a collision between 2 brains. When they slammed into each other, the energy of the impact turned into matter, radiation, space, and time. Our universe ignited. After the collision, the brains bounced apart and the universe began expanding. But they're still drifting in that higher dimensional space. And one day, billions or trillions of years from now, they may collide again. Another bang, another universe, another cycle. Each collision would be a cosmic reset, new physical conditions, new laws, new possibilities, and maybe, just maybe, traces of the previous universe survive the crash, in subtle imprints, in patterns of temperature across the sky, in gravitational waves echoing through the void. Some physicists believe that if we look closely enough, deep into the cosmic microwave background, the faint afterglow of the Big Bang, we might find evidence of a previous brain collision, scars, echoes, messages from before time began. But brains do more than offer a new view of the Big Bang. They challenge our entire idea of what before even means. If time itself began with our Big Bang, how can we speak of before? Well, in brain cosmology, time may be emergent, a property that arises only when brains interact. In the space between, time as we know it may not exist. Instead, there's only the geometry of higher dimensions and the rhythm of approaching sheets. So instead of asking, what was there before the Big Bang? We can ask, where was our brain before it collided? How long did it drift through the bulk, this higher dimensional space? And how many times has it collided before? We don't yet know, but what we do know is that brains offer a tantalizing answer. The Big Bang wasn't a one-time miracle. It was one of many sparks in an endless dance of universes. It means our universe isn't an island. It's part of a larger ocean, a multi-dimensional realm we can't see, but may one day understand. It also opens the door to another idea, that the Big Bang is not the only way a universe can begin, that there may be ways for space and time to tunnel into existence from nothingness itself. And that takes us deeper into the world of quantum beginnings. Let's pause. Take a deep breath. We've journeyed from cosmic bubbles to colliding brains, from infinite inflation to higher dimensions. But now, we reach the strangest idea of all, one that whispers, the universe may have come from nothing, no matter, no space, no time, just nothing. And yet, from this nothingness, everything we know was born. This idea isn't just poetic, it's rooted in quantum physics, where empty space isn't really empty, and nothing is far stranger than it sounds. You see, in quantum theory, even a perfect vacuum isn't truly void. It seethes with invisible activity. Tiny particles flicker into existence, then vanish, too quick to see. These are called quantum fluctuations, and they're happening everywhere, all the time, even in the most silent corners of space. Now imagine this. If particles can pop in and out of existence, why not space itself? Why not time? Why not an entire universe? Welcome to the idea of quantum tunneling from nothing. A bold and brain-bending proposal. It starts with a concept known as the false vacuum, a state that appears stable, like a marble resting in a dimple, but which actually sits on the edge of something deeper. Given time, that marble can tunnel through a quantum barrier and fall into a true vacuum, a lower energy state. When that happens, the vacuum can explode, creating a bubble of expanding space. That bubble could be a new universe, our universe, our universe. In this theory, the cosmos didn't arise from an existing brain or from a fiery singularity. It tunneled into existence through a kind of cosmic quantum leap, from literally no space and no time, into the space and time we now live in. Some models, like the Hartley-Hawking no-boundary proposal, suggest that the universe had no edge in time, no beginning, no singular point of origin. Instead, time gradually emerged from a timeless quantum state, like the smooth surface of a sphere where there is no true starting point, just a continuous, rounded geometry. In their picture, the universe is finite but unbounded. It didn't pop into existence suddenly like a firework. It gently emerged like mist from a sea. Others, like physicist Alexander Vilenkin, proposed that the universe did have a beginning, but that this beginning was a quantum event, a spontaneous birth from the void. One moment there was nothing. The next, a tiny, high-energy pocket of space inflated into everything we see. But how can nothing cause something? That's where things get slippery. In quantum mechanics, events don't always require causes in the classical sense. Particles can appear without a reason, just as a matter of probability. So perhaps the same is true for the universe. If the laws of physics themselves are allowed to exist outside of time, they may not require a cause at all. They simply are. And from them, all else follows. Still, some scientists and philosophers push back. They ask, can we really call the quantum vacuum nothing? Is a mathematical possibility the same as a physical reality? If laws of physics exist before the universe, then is that really nothing? Others argue that these questions may be meaningless. that time itself only exists inside the universe. Asking what happened before time may be like asking what's north of the North Pole. Still, these models offer a strange kind of comfort, because if the universe can emerge from nothing, then perhaps this entire cosmos is the result of a cosmic inevitability, not a miracle, not a mistake, but a natural outcome of the way the quantum world behaves. In this view, nothing isn't the absence of everything. It's the possibility of anything. A blank canvas so rich with potential, it gave rise to all the stars, all the galaxies, and all the hearts and minds that now wonder where it all began. So where are we now? We've explored the universe as a bubble, as a brain, as a quantum ripple. We've seen it as a cycle, a branching tree, an explosion, and an emergence. Each model gives us a piece of the puzzle. Each one pushes the boundary of what beginning even means. And now we come to a final mystery, a place where science meets philosophy, where observation stops and speculation begins. Because the next question is this: even if the universe can come from nothing, why is there something rather than nothing? That's where we'll go next. So here we are. We've flown through models of the cosmos that sound like riddles, danced among brains and bubbles, wandered through time before time, and now we arrive at the final question. A question so simple, a child might ask it, yet so deep, it leaves even the wisest thinkers in silence. Why is there something rather than nothing? Why anything at all? Not just why the Big Bang happened, or how inflation worked, or what existed before, but something even more basic. Why there is a universe and not a perfect, eternal silence. Let's try to unpack this. First, it's important to understand this is not a scientific question in the usual sense. We can model how the universe expanded, how stars formed, how matter clumped together. But why existence exists goes beyond physical equations. It's closer to philosophy, or poetry, or awe. Some thinkers argue that nothing was never an option. They say that nothingness, true, total, absolute non-existence, is unstable or even impossible. That if any kind of law or logic can apply to it, then it's not really nothing. It has rules. And once rules exist, things can follow, like universes. Others believe the universe exists simply because it can, that all possible realities are equally real, that anything not forbidden by logic eventually comes into being. In this view, our universe is just one of the possible ways existence can unfold. Maybe all possibilities happen across infinite time, across the multiverse, or through some unknowable landscape of being. We live in this one because, well, here we are. Still others say we asked the wrong question. They argue that nothing is not the natural state. Something is. Because once there's a possibility, it's only a matter of time before it happens. Or maybe there's no time, no chance, no cause, just existence, uncaused, undesigned, unasked for. And yet, here it is. Now let's consider something deeply personal. The idea that observers are part of the answer. You, me. The very fact that someone is here to ask why is part of the explanation. This is related to what scientists call the anthropic principle. It says that the universe must be the kind of place where observers can exist, because otherwise no one would be around to notice it. We find ourselves in a universe with the right conditions for life, because only such a universe allows anyone to ask questions in the first place. It sounds circular, but it might be the best answer we can get. In other words, we don't live in this universe because it's special. We live in it because we're alive. If the cosmos was slightly different, if gravity was stronger or atoms didn't hold together, then stars would never form, planets would never coalesce, life would never rise. No telescopes, no stories, no one to wonder why. It's as if reality filtered itself through the eye of life, and we are what passed through. Now, zoom out for a moment. Imagine trillions of universes, each with different rules, different dimensions, different histories. Most are barren. Some collapse instantly. Others stretch into cold nothingness. But one, ours, formed stars, atoms, oceans and minds that ask questions. And in this sea of possibilities, our universe lit up. Still, none of this fully answers why. It only shifts the mystery. If the universe exists because it can, why can it? If there are laws of physics, why those laws? If we exist to observe, why is observing possible? And here, the trail fades into silence. It's possible that this final why is unanswerable. Not because it's too hard, but because it's not a scientific question at all. Maybe existence is a brute fact. Maybe it's a miracle. Maybe it's just what is. Or maybe one day, far in the future, we'll find a new kind of understanding, a deeper law, a broader theory, a way to show that the universe must exist, that nothingness is not real, and that everything, space, time, matter, life, is woven into a single, necessary truth. But until then, we do what humans have always done. We look up at the stars, we build telescopes, we dream, we ask, and we keep searching for answers, knowing that the question itself is part of what makes us alive. So why is there something rather than nothing? Maybe because that's the most beautiful thing there could ever be. Now that we've wandered through deep questions of existence, why is there something rather than nothing? Let's gently return to firmer ground. Let's go back to the observable universe, the one we can see with telescopes, map with satellites, and explore with mathematics. Let's rewind our cosmic movie, not to the moment of nothing or the metaphysical why, but to the earliest frame of time that science can truly speak about. Welcome to the Planck epoch, the first 10 to 43 seconds after the birth of our universe. That's 0.000, 43 zeros. 1 second, a time so small it barely exists. A time when the universe was smaller than an atom, hotter than a billion suns, and governed by physics we still don't fully understand. This era is called the Planck era, named after Max Planck, one of the founding fathers of quantum theory. At this scale, the universe was ruled by quantum gravity, a theory we don't yet possess. Our known laws, general relativity and quantum mechanics, both break down at this point. They scream for reconciliation, but they won't cooperate. Relativity describes the smooth curvature of space and time. Quantum theory describes jittery uncertainty, randomness, and probabilities. But in the Planck epoch, both are required, and both fail. So what do? We imagine, we model, we guess. We propose theories like string theory, which says all particles are tiny vibrating strings of energy, resonating at different frequencies like notes on a cosmic violin. We explore loop quantum gravity, which imagines that space and time are made of tiny loops, discrete building blocks of geometry. But we don't yet have proof. Still, we can peer just after this moment into the next stage of cosmic evolution. And that's where things begin to clear up. Around 10 to 36 seconds after the Big Bang, something astonishing happens. The universe undergoes a sudden, incredible growth spurt. It inflates. This is called the inflationary epoch. In a fraction of a second, the universe expands faster than the speed of light, not because matter is moving, but because space itself is stretching. Distances between points increase exponentially. If the universe were the size of a proton before inflation, it becomes the size of a grapefruit, then a beach ball, then a galaxy, all in less than a blink. Why is this important? Because inflation solves several big problems in cosmology. 1. The horizon problem. Why is the universe so uniform in all directions? Without inflation, distant parts of space couldn't have communicated with each other. But inflation says they were once close, then stretched apart. 2. The flatness problem. Why is space so perfectly flat, not curved like a saddle or a sphere? Inflation flattens space, like pulling a balloon tight. 3. The monopole problem. Why don't we see magnetic monopoles or other weird relics from the early universe? Inflation dilutes them out of existence. But inflation does something even more important. It plants the seeds of structure. During inflation, tiny quantum fluctuations, minuscule blips of energy, are stretched out to cosmic scales. They become the first wrinkles in space, regions slightly more dense than others. After inflation ends, these wrinkles attract matter. They grow. They form galaxies, stars, and eventually planets and people. So, everything you see, the Milky Way, the Andromeda Galaxy, your hands, your thoughts, can be traced back to quantum jitters during inflation. Think about that. The randomness of the quantum realm gave birth to everything structured in the universe. Order from uncertainty, cosmos from chaos. And what happens after inflation? The energy driving inflation decays, heating up the universe in a moment called reheating. This floods space with radiation and particles, quarks, gluons, electrons, photons. The beginning of the hot Big Bang phase. From here on, the universe behaves like a hot, dense soup of particles, cooling as it expands. In the next few minutes, the first atomic nuclei form, mostly hydrogen and helium. In the next 380,000 years, atoms themselves come together, and the universe becomes transparent for the first time. Light is finally free to move. That light, those ancient photons, are what we detect today as the cosmic microwave background, the baby picture of the universe. So from the mystery of nothingness, we've arrived at something astonishingly solid. We know when light broke free. We know how galaxies formed. We can trace it back to fractions of a second after time began, but we still don't know what started it. Inflation helps, but what started inflation? What caused the first fluctuations? And what was the Planck epoch really like? To answer that, we'll need to unite gravity with quantum theory. We'll need a new kind of physics. We'll need to go beyond Einstein, beyond Schrödinger, and that is the realm of quantum cosmology, which we'll enter next. Now, as the glow of the early universe fades and galaxies begin to take shape, we step into one of the most mysterious frontiers in science, quantum cosmology, the study of the universe's birth through the lens of quantum mechanics. You might be wondering, how can quantum physics, which describes things smaller than atoms, help us understand the entire universe? Well, imagine this. At the very beginning of everything, the universe itself was smaller than an atom, smaller than a proton, maybe even smaller than space and time themselves. So to understand where the universe came from, we can't just look at stars or gravity. We have to shrink everything down until we see the flickering, uncertain, rule-bending world of the quantum. And this is where things get truly weird. Let's introduce a bold idea. What if the universe came from a quantum fluctuation? Just like particles can suddenly appear and disappear in empty space, borrowed from the vacuum through quantum uncertainty, maybe the entire universe sprang into existence the same way. This idea isn't just science fiction. It's taken seriously by many physicists. In quantum field theory, the vacuum isn't truly empty. It bubbles with activity, particles popping in and out of existence, energy fields trembling with uncertainty. This restless quantum foam might be the key. Physicist Edward Tryon famously said in 1973, "Perhaps the universe is simply one of those things that happens from time to time." Let that sink in. What if the universe was a quantum event, a blip, a spontaneous fluctuation in a deeper field of reality, one that just didn't fizzle out, but instead of collapsing, this fluctuation inflated, stabilized, and became all of this: you, me, galaxies, poems, mangoes, mistakes, memories, all from a twitch in the quantum void. Now, for that to happen, something curious must be true. The total energy of the universe must be zero. It sounds strange, but it might be right, because gravity has negative energy, and all the matter and radiation we see, stars, planets, black holes, have positive energy. When you add it all up, they might cancel out perfectly. A kind of cosmic accounting trick. If that's the case, then a universe could be born from nothing without breaking any laws. Nothing would be borrowed, nothing would be owed. It would be, in a strange and subtle way, free. Now, let's bring in another mind-bending concept: the universe as a quantum wave function. Physicists James Hartle and Stephen Hawking proposed something extraordinary in the 1980s. What if the universe has no beginning in time as we understand it? They suggested a model where time itself smoothly curves into space, like the surface of the Earth curves around the South Pole. In this picture, there's no sharp starting point like a Big Bang singularity. Instead, the universe just rounds off. This is called the no-boundary proposal. According to this idea, time becomes space-like near the origin, so there's no edge, no wall, no before. It's like asking what's south of the South Pole. There's no answer, because it's not a valid question. In the same way, asking what came before the universe might not make sense. There was no before. Time itself emerged, along with space, matter, and the laws of physics. And the entire cosmos, past, present, and future, might be described by a single wave function, a timeless probability cloud that contains all possible realities. Now, this is hard to grasp. It's not something you can draw, not something you can see, but it might be the most accurate picture we have. The universe didn't start in a flash of lightning. It emerged softly, like mist condensing into form, like a wave rolling into being from a calm sea. So where does that leave us? We've gone from timeless possibilities to quantum ripples, to inflationary expansion, to a universe full of stars, galaxies, and life. And behind it all, a strange truth. The universe might not be a thing that happened once. It might be a pattern, a quantum dance that simply is. And we, tiny beings of carbon and questions, are entangled in that dance. We don't just observe the universe. In some mysterious way, we participate in its unfolding, not because we control it, but because we are it, born from it, made of it, asking questions that arise from within it. And maybe, just maybe, those questions are part of the answer. In the next section, we'll return to the cosmic microwave background, the echo of creation, and see how this ancient light reveals the deepest truths about our origins. But for now, just breathe and know the fact that you're here, reading this, Thinking these thoughts, it itself is one of the universe's greatest miracles. We've surfed the edge of time and plunged into quantum mist. Now let's turn to something more grounded, something we can actually see, not with our eyes, but with our instruments. A glow, a faint whispering light that has been traveling for over 13 billion years. It's called the Cosmic Microwave Background, or CMB, and it is the oldest light in the universe. Think of it like the afterglow of a campfire, long after the flames have vanished. This light is the fossil of the Big Bang, and it contains secrets about how the universe began, what it's made of, and maybe, just maybe, what lies beyond. Let's go back to a time before the stars, before galaxies, before atoms. Just 380,000 years after the Big Bang, the universe was a hot, dense plasma, a soup of particles and light. Photons, particles of light, kept bouncing off electrons and protons, like sunlight through a fog. But as the universe expanded, it cooled. Eventually, the electrons and protons slowed down enough to stick together, forming hydrogen atoms. And in that moment, the fog lifted. Light was free to travel. That light is the CMB, and we can still detect it today, filling every corner of space, coming from all directions. It's incredibly cold now, just 2.7 degrees above absolute zero, but it's there, like the universe's baby photo. In 1965, two scientists, Arno Penzias and Robert Wilson, accidentally discovered this glow while trying to fix a strange hum in their radio antenna. They thought it was pigeon droppings. Turned out, it was the universe speaking. Later missions, like COBE, WMAP, and Planck, gave us high-resolution maps of this ancient light. They revealed subtle temperature fluctuations, tiny variations in density, ripples in the early universe. These ripples eventually became everything: galaxies, stars, planets, you. But here's where it gets even more amazing. Those tiny ripples in the CMB match predictions from inflation theory. Remember inflation? That ultra-fast expansion right after the Big Bang. It turns out, inflation didn't just stretch the universe, it stretched quantum fluctuations, turning microscopic randomness into macroscopic structure. So when we look at the CMB, we're seeing quantum fingerprints writ large across the sky. The oldest light, the tiniest causes, the grandest effects, and there's more. The CMB doesn't just tell us about the past, it tells us what the universe is made of right now. By analyzing its patterns, scientists have learned the universe is about 13.8 billion years old. It's made of 5% normal matter, the stuff we see and touch. 27% is dark matter, invisible, mysterious, but detectable through its gravity. And 68% is dark energy, the force causing the universe to expand faster and faster. That means 95% of the universe is still unknown. Now pause and breathe that in. We live in a universe that has revealed so much, yet remains mostly hidden. The CMB shows us the edge of visibility, but not the edge of understanding. In fact, some researchers believe the CMB might contain subtle hints of things beyond our universe. For example, anomalies in the CMB, cold spots, alignments, could be clues of other universes brushing against ours. Patterns in polarization might help us detect gravitational waves from inflation itself, echoes of the universe's birth. And future telescopes might even map the quantum seeds of existence. It's like standing in an ancient cave, looking at wall paintings drawn by light itself. We don't fully understand the language, but we know it's telling us something true. And perhaps the most beautiful part? This light has traveled for billions of years, through space, through time. to land gently on your eyes, or your telescope, or your screen. It's the past, arriving now, a direct line from the beginning to this moment, from the unknown to the known, from chaos to cosmos, from nothing to you. So next time you look at a star or sit in the dark and wonder where you came from, know this: the answer is written in the sky, faint and cold, but still shining, still singing the first song the universe ever played. And we are finally learning to listen. We've seen the quantum seeds. We've listened to the universe's first whisper, the cosmic microwave background. Now let's look farther, wider, deeper. Let's ask the question that almost everyone wonders, but few dare to imagine clearly. Is this the only universe? Because what if it's not? What if our entire universe, everything we know, from the smallest atom to the largest galaxy, is just a bubble? One bubble in a vast, frothing ocean. Welcome to the idea of the multiverse. It might sound like science fiction, but the multiverse isn't a fantasy. It's a serious scientific proposal that arises naturally from some of the theories we've already explored. Let's go back to inflation. In the simplest versions, inflation happens all at once and then stops. But in many models, it never really ends everywhere. Instead, inflation ends in some regions, forming bubble-like universes like ours. But it keeps going in other regions, endlessly expanding space and creating more bubbles. Each bubble becomes its own universe, with its own laws of physics, its own constants, its own story. This is called eternal inflation, and it leads naturally to the idea of a multiverse, a cosmic foam where universes endlessly form and drift apart. Now, imagine this. Some universes might have no stars. Others might collapse a second after forming. Others might have different versions of gravity or no atoms at all. And some might be almost like ours, but with slight variations. Maybe there's a universe where the dinosaurs never went extinct, or where the Earth has two suns, or where another version of you is reading this with purple grass outside your window. It's not guaranteed, but it's possible, at least according to some of our best mathematical models. Let's go further. The multiverse isn't just one idea, it's many. There are several kinds of multiverses proposed by physicists. 1. The inflationary multiverse. As we just saw, this arises from eternal inflation, bubbles everywhere. Each bubble a universe. Possibly infinite, probably unobservable, except maybe through rare collisions that leave marks in the CMB. 2. The quantum multiverse. Remember quantum mechanics, how particles can be in multiple states at once. In the many worlds interpretation, every quantum choice creates a branching of the universe. You go left, that's one world. You go right, another. Every possibility happens somewhere, infinitely branching paths, infinitely branching yous. In this view, the multiverse isn't out there. It's branching within our universe, every moment. 3. The string theory landscape, each with different physical laws. This landscape could be populated by universes, each one like a different valley in a vast mountain range. Our universe would be just one valley, a spot where the conditions happen to be just right for life. Why here? Because here is where observers can exist. This leads us to a powerful and slightly uncomfortable idea, the anthropic principle. It says, we see the universe the way it is, because if it were different, we wouldn't be here to see it. Imagine a lottery with trillions of possible outcomes. Most are barren, lifeless, chaotic, but a few are just right. And we, living, thinking beings, can only appear in those few. So it's no surprise that we find ourselves in a universe with stars, atoms, chemistry, and comfort. But maybe it's not special. Maybe it's just one of many, just the one where we happen to exist. Now, take a deep breath. This is where science meets wonder, because if the multiverse is real, it changes everything. It means the laws of nature might not be fixed. It means our universe is not the center, not even the main event. It might be just a ripple, just a note, just one story in an infinite library. And yet, even if we're just one bubble, one quantum flicker, one moment in a vast sea, that doesn't make us less. It might make us more, because in all that cosmic foam, in all that possibility, you are here, alive, aware, wondering. And maybe that's the rarest thing of all. In the next section, we'll ask a question that touches philosophy as much as physics. Can the universe explain itself? Or are we reaching the edge, not of space, but of knowing? We've wandered through quantum ripples, surfed the first light, and peeked into the possibility of a multiverse. Now comes a more haunting question, one that echoes not in the stars, but deep inside the mind. Can we ever truly understand the universe? Or are there limits, edges, not of space, but of human knowing? Let's begin gently with a thought experiment. Imagine a fish born in a deep ocean trench. It has never seen the surface, never felt air. For it, water is not something to notice, it is the only thing. Now imagine trying to explain sky to that fish. Hard, isn't it? What if we are like that fish? What if we're swimming inside a universe whose deepest truths we're not built to grasp? Let's explore a few reasons this could be true. 1. Cognitive limits. Human brains evolved to hunt, gather, and survive on the savannah. We're good at throwing rocks. We're not optimized to understand 10-dimensional string fields or quantum tunneling events. Yes, we've come a long way, with math, models, and machines. But there's a real chance that some truths are just beyond our cognitive ceiling. Not because they don't exist, but because we're simply not wired to think that way. Imagine a dog trying to grasp algebra, or a pigeon inventing calculus. It's not about intelligence, it's about framework. Maybe our framework just isn't enough. 2. Tool limits. Even our best instruments, the James Webb Telescope, quantum colliders, gravity wave detectors, they all have limits. There are regions of the universe we can't see, beyond the cosmic horizon, where light hasn't had time to reach us. Inside, black holes, where information disappears. At the Big Bang itself, where equations break down. These aren't just technical gaps. They might be fundamental boundaries, cosmic censorships built into reality. So even if we ask the right questions, we may never hear the answers. 3. Mathematical incompleteness. Here's a subtle, profound one. In the 1930s, a mathematician named Kurt Gödel showed that any complex mathematical system will contain statements that are true, but can't be proven within that system. This is called Gödel's incompleteness theorem. It means there will always be truths that escape our models. Now apply that to physics. If the universe is describable by math, as we believe, then some parts of it may always remain beyond proof, knowable in principle, but unreachable in practice. It's not a glitch. It's baked in. So, is that it? Are we doomed to gaze at the universe like a moth staring at a light bulb, forever dazzled, never understanding? Maybe, but maybe not. Because there's another way to think about this. A more humble and perhaps more beautiful idea. We don't need to understand everything to be in awe. After all, A child doesn't need to grasp quantum mechanics to marvel at the stars. A bird doesn't need to know aerodynamics to fly. A heart doesn't need to know anatomy to feel love. What we've learned already is staggering. We've uncovered the age of the universe. We've traced atoms back to stardust. We've predicted black holes, seen gravitational waves, and mapped invisible matter. We've done this from a speck of rock orbiting a middle-aged star with nothing but fragile minds and telescopes made of glass. We may never know everything, but look how much we know already. And that brings us to one last truth. Sometimes what matters most isn't what we know, but how we wonder. Because curiosity isn't just a tool, it's an act of hope. To ask questions of the universe, even when the answers may never come, is to say, I'm here, I care, I'm listening. So maybe the universe doesn't explain itself. Maybe it doesn't owe us clarity or closure, but maybe we're not here to solve it. Maybe we're here to witness it, to look up at the night sky and not just see stars, but feel them, feel the immensity, feel the mystery, and know that even if the final equation never arrives, we were part of the story. We wondered, we searched, we reached, we loved. In our final section, we'll slow down. We'll take everything we've learned about atoms and galaxies, about beginnings and ends, and carry it gently into silence. A quiet descent from the stars, back to the heart. So now, after wandering through cosmic dust and colliding galaxies, after pondering quantum seeds and infinite bubbles, after asking impossible questions and leaning into silence, we arrive here, at the end of the story, but also the beginning of something softer. Not knowledge, not facts, but a quiet kind of understanding. Let's go back to the moment the universe began, a single instant, a nothing that became everything. In that one heartbeat of time, the laws of physics were born. Time began to tick, space stretched, energy cooled, matter condensed, and billions of years later, here we are. You, sitting, reading, breathing, thinking about all of it. What a journey that has been. From the fire of the Big Bang to the fire behind your eyes. When we say we are made of stardust, it's not a metaphor. The calcium in your bones, the iron in your blood, the carbon that knits your thoughts together, all of it was forged in stars. Stars that exploded before the Earth was born. You are not just in the universe, you are of it, an extension of its memory, a flicker of its consciousness, a question it asks itself. And that changes everything, because it means that when you wonder about the universe is wondering about itself. Maybe that's the real meaning behind all this. Not just particles, not just equations or telescopes or dark matter maps, but connection. The Big Bang wasn't just an explosion, it was a birth, and everything that followed, planets, trees, music, pain, joy, curiosity, is part of that same unfolding story. Sometimes we feel small. The universe is so large, so old, so cold. But you are not small, not really. You are the only thing that can feel how large it is. You are the flame that lights the darkness. You are the silence that listens. You are the voice that says, wow. And if that's not powerful, nothing is. So what now? Now we rest. We let go of trying to figure everything out. We stop grasping for answers. We stop fighting the unknown. Instead, we let the mystery be our comfort. Like a night sky full of stars, unknowable and still beautiful. You don't need to know how it all ends, or what came before the beginning. or what lies beyond the edge. Just know this: you were here, in this universe, on this planet, in this moment, full of light and life and wonder. So close your eyes. Let the galaxies keep spinning. Let time keep flowing. Let space keep stretching. You've done enough wondering for today. The universe will still be here tomorrow, and so will you. Now, let the stars grow quiet. Let the galaxies drift like lanterns across the night. You don't need to understand it all. You don't need to hold the whole universe in your thoughts. You've already done something incredible. You opened your mind to the vastness. You let your heart wander across light years. And now, it's time to come home. Feel your breath. Slow, gentle, like waves in a calm black sea. You are safe. You are stardust wrapped in warmth. You are the quiet spark that wanders and dreams and rests. Far above, galaxies continue to swirl. Stars are being born, even now. And still, here you are, lying still, breathing in silence, letting go. You don't need to chase the answers anymore. Not tonight. You've asked your questions. You've followed the stars. Now, let them keep moving. Without you for a while. Let your body soften. Let your thoughts dissolve like mist. Let the weight of wonder turn into something feather-light. Because the universe doesn't just speak in explosions or equations. It also whispers, in dreams, in stillness, in sleep. So rest now, traveler. You are a part of it all. The dark, the light, the story, the silence. Good night, and good stars.